you can hear me on the microphone? If everybody could start making their way back, we're going to move on to the next portion of today. Oh, God, I'm sorry. I need to do that. Well, thank you all for joining us at the first annual Energize NRT Symposium. I'm pleased to introduce our speaker today, Jeffrey Neaton. As you may know, the planning and organization of this symposium was student-led, and we chose Professor Neaton as our plenary speaker because his group's work is at the intersection of machine learning, material science, and engineering. And so we felt that with his group's interdisciplinary studies in the context of energy applications, that their work really centers the theme of today's symposium, data-driven discovery in sustainable energy materials. Professor Neaton is a professor of physics at UC Berkeley, a senior faculty scientist in the Materials Sciences Division at the Lawrence Berkeley National Lab, and is a member of the Kavli Energy Nanosciences Institute at Berkeley. Jeffrey Neaton earned his PhD in physics from Cornell in 2000 and was a postdoc at both Rutgers University and the Lawrence Berkeley National Lab. He was a recipient of the DOE Presidential Early Career Award for Scientists in 2009 and was named a Fellow of the American Physical Society in 2013. He received the NERSC High Impact Scientific Achievement Award in 2017 and was also named the Pariser Parr Distinguished Lecturer in Chemistry at UNC in 2018. Lastly, among many other achievements, he was named an American Physical Society Outstanding Referee in 2023. So if you could please join me in welcoming today's speaker, Jeffrey Neaton.
Thank you so much. Yes. Much. So can you hear me? Is this okay? All right. So really appreciate the very, very kind introduction, and I think it's really an honor to be invited by this group. So thank you for the opportunity to be here and to talk a little bit about this topic, which is a fun topic, and we're doing, we have increasingly worked in machine learning, and I'll talk a little bit about that. But I really have to say the first two speakers did a terrific job of introducing so many things that are, I think, topical right now, so it will make my role a little bit easier. So really wonderful to be here. Look forward to the rest of the symposium as well. So I think just to start, I probably reiterate a few points that were already brought up. And that is that we're kind of in a, we're in this sort of, I don't know, it's sort of a cliche, but we're in some kind of inflection point, I guess, with AI, where it is increasingly infiltrated our lives at home, but also at work. And there are some interesting opportunities, I think, for research in materials and other domains. And actually, I think it's still an open, as you're seeing from these talks, I think earlier, there's a lot of research in how AI can help our research that needs to be done, if you get what I'm saying. So I think, but it's really, there's a lot of potential. So these are some examples of, automated laboratories that are going autonomous at some level, being reported as such, and AI agents being deployed in a materials context. So you're starting to see this in the literature. And then I think, as was mentioned, that has created a lot of excitement, so much excitement that startup companies are jumping in, and there's a lot of funding for that, and we'll see how that all goes. But I think that just sort of underscores its promising aspects, and I think in our space we're trying to do science with these tools. It is a tool, and so we're trying to figure it out and do science with it. And I think whether or not AI can really help us discover new materials is still a question, I think, but it is one that is very interesting to pursue and think about for this community. I would say, though, in terms of answering that question, it's really going to come down to the data sets, and the way these all things are trained. I think probably everyone would agree with that. And materials, there's a lot of heterogeneous data in laboratories and computation. But one area, and this kind of brings it back toward my expertise, which is in computation and theory, if you like, and it's been discussed in the talks that we've seen. One area that I think we've seen more fair or perhaps just organized databases is in theory. So these are some examples of large-scale databases of DFT calculations at some level of theory. And many of these databases include more than 100,000 structures, or depending on what literature you're looking at, millions perhaps. But that data, which is in an organized way with all the metadata and properties, has really been part of what is starting to enable the things I was talking about on the previous slide. But one of the biggest recent achievements of those databases has been the machine learning interatomic potentials that were spoken about by Professor Schindler earlier. The fact that we can now you can evaluate DFT with DFT-like accuracy models that scale linearly with the number of atoms rather than kind of cubically is a direct result of the data sets on the left. And so, having, I guess, as more, unique, validated, high-quality data sets appear, we'll be able to do even more things. But I would argue I don't argue, I would just state that they're not there yet. We're not quite there yet, and that's something that our community will have to sort of think about how to do. Maybe there's also some additional discussion topics about, sharing data, and, it's, sort of there are different communities like high energy physics or astronomy where data is more readily shared, in materials and chemistry a little bit less so. So anyway, meta discussion for later. But in any case, I think in the area of theory, there's been an advance because of the presence of these data sets. And so I think that does kind of create some opportunities in the energy materials regime. And I wanted to just, here's some kind of examples at a high level that are going to tie into some of the things I talk about. But in terms of efficient electronics and trying to, the sustainability is in the center's mission here. So just talking about, kind of using material, getting the elements that you need to make materials from a sustainable source, and also some of the more, kind of longer-term energy technologies like solar fuels. I think, there's real opportunities for materials. And I think, of course, we need data to take advantage of AI, but I also think we need more theory. And this is the other point I wanted to say, is that it isn't all data and AI at this point. And that's because many of the properties that kind of are critical to the function of these technologies tend to be spectroscopic, or they're finite temperature. There was a discussion, I think it was mentioned, they're not perfectly crystalline. That's the other thing. But there's also dynamical properties. And those aren't really readily accessible in the databases I just showed you. Those aren't really tabulated. And so I think there's a need for doing that theory, and there's also a need for some predictive workflows that compute those observables at scale once we've got that. So, and then I have these little people here because I don't think the human is out of the loop at this point. And I don't see that in the foreseeable future, but I don't want to extrapolate too far. But I think humans are still going to be important, because as far as I've been, in my interactions with the AI, the prompt matters a lot. And so I think at this point, and I'll talk about that a little bit in my talk. So this talk, just to be a little bit more concise, is going to be focused on talking a little bit about some new observables that we're calculating relevant to energy materials, hot off the press theory, some new workflows for calculating some new observables more efficiently, and then I'll talk a little bit about some of our experiences with MLIPs as well. I'm going to focus on really two classes of materials. So there's going to be materials in this talk, and I appreciated that there wasn't in the previous one. I think that was a good, I really liked that, but there will be, materials are coming back. So I have to be on theme here. So I'll talk a little bit about photophysics of light absorbers, and then I'll discuss small molecule and critical element captured by porous materials and what we can do with this combination of techniques there. So a pretty famous light absorber is silicon. That's what I mean by light. It's an example of a light absorbing material, and it dominates the solar cell market. But it's not the only material that is in technologies for solar cells. So there are many other kinds that are used, and that's because silicon, although it has a band gap that makes it pretty optimal for the kind of sort of theoretical, it leads to a high theoretical efficiency that can be achieved with sufficient processing in the lab. It tends to be, it's an indirect gap semiconductor, and so you need a really thick amount of silicon, and it's on the heavier side compared to some of the things I just showed. And so even though it's pretty commercially viable, and I have some in my roof back in California, solar panels with silicon, there are other materials that are being explored, and one of them are these halide perovskites that you may have also heard about. That there's been a lot of interest in the last 15 years, and that is actually a direct gap system. It can be much thinner, and it's also instead of the high temperature processing to remove defects that is required for silicon. It's sort of solution-based processing. So you can kind of assemble the thin films much more cheaply. Some of these do include lead, so that's on the other side of it. But that is really driven its sort of relevance and use. And one of the things I wanted to point out about that particular system, I'll come back and talk about these a little bit, is that over the last 15 years, and there's actually a period of about 6 or 8 years since it was understood to be, it was kind of identified as an interesting light absorber. There was tremendous progress increasing its efficiency to a point that's very close to the theoretical max. So over just like 6, 7, 8 years, this material was, hey, it's got a great band gap, could be cool for solar. Yep, it's really cool. Yep, we can get 25%. And now there's tandems with 34% efficiency. So this growth curve, it's still in years. This isn't, so for those who do a lot of machine learning, this isn't minutes. It's still years, and it's quite a few years. But I think one of the takeaways of this first part of what I'm trying to say is that there's a lot of room for new materials. And there has been some accelerated development of those materials. And perhaps, if we can harness AI, responsibly and understandably, we could even reduce that time. So let me talk a little bit. So I'll show you some results that were, and calculations and some hopefully intuition that we're using. So, but I want to talk about what the ground truth is in our calculations. So we'll start there, and this is a sort of our theoretical framework that we've been using. And I'm going to talk in this first part of this talk about spectroscopic properties, about light absorbing and such. And I'm going to be talking about that in extended systems. So I should caveat this is really what I would consider a kind of a state-of-the-art workflow for crystals. And so it starts with density functional theory, but it also requires beyond DFT methods, because we heard a little bit about this, but DFT doesn't do very well for gaps. It's a more subtle discussion. I'll kind of get into it a bit more. But more appropriate sort of theory of excitations kind of involves Green's functions, et cetera, and that kind of goes under the many-body perturbation theory, GW, beta salpeter equation approach calculations. So this allows us to compute, and I'll talk about in a second, photoexcitations, photoexcitation energies, and other properties. So one of the things I wanted to start with is, as I mentioned, there's kind of a need for calculating new observables, not just, kind of more data with existing approaches. And one of the things about this framework, which I would consider state-of-the-art for materials, is that everything is at t equals 0. And so, you might think, well, there are electrons and they're pretty high energy and t equals 0 doesn't matter. But I'll show you in a second, that's actually kind of an important simplification that isn't, that we wanted to relax. And so one of the things I'll show you a little bit is some progress we're making capturing temperature and lifetime and the effects of lattice vibrations, which are obviously connected to temperature and phonons. So let me say a few words about these excitations quickly, kind of in a high-level way that I'm going to be focused on for the next little bit in the talk. So if you shine light on a material and it's got translation symmetry, and you can think about band gaps and valence and conduction bands, then you're essentially, in the kind of classical theory, you're exciting an electron out of the valence band into the conduction band, and that leaves behind a hole, and they can interact. And that interaction in the simplest model would just be kind of hydrogenic. It's like a modified hydrogen atom, except one of the components is much lighter than the proton, and that leads to this mu effective mass. And it lives in a solid, and so it's got a dielectric constant in the denominator. So essentially you have the Rydberg with this modification that involves the effective mass and the screening. And so when you shine light on the system, that electron hole are bound. Often to make the material functional, you want to separate the electron hole. So it's kind of relevant. This binding energy is sort of a relevant quantity for these materials. And so just to give you a sense for these are certain set of materials. These are two types of perovskites, I guess on the left, and an organic crystal and a 2D material on the right. And you can see the binding energies in millielectron volts listed here. And so it's critical to hear that these binding energies kind of straddle KT at room temperature. So KT at room temperature is 25 millielectron volts. And so you could imagine that in neglecting any kind of lattice effects or temperature effects might not be very a good approximation. But that is actually the state of the art. So this is something we wanted to advance. And so basically, I'll try to show you pictorially what I think sort of summarizes the physics of this. So if you think about how does temperature affect one of these excitons, this bound electron hole pair, it's really how do phonons affect it? So that's one way to kind of translate that question. And so how do phonons affect an electron hole pair? Well, there's a few different ways. They affect the individual constituents. So you can imagine that phonons will interact with the electron, they'll interact with the hole, and they'll change the electron hole energy and the nature of the wave function and such, and that would change how they couple in this exciton. And that's they also if the lattice vibrations are polar, they can screen the electron hole interaction, so they can actually contribute to the dielectric function, the dielectric constant in the screening environment. And then, if the interaction is strong enough, they can distort the lattice away from its equilibrium positions. And so these are sort of three basic ways in which that phonons can interact with the electron, the exciton. And one of the things we've been doing is developing new methodologies, ab initio methodologies, to look at two of these different ways, which are valid in a slightly weaker coupling regime. And so kind of developing the machinery to calculate this. So we're not doing this high throughput. We haven't introduced machine learning, but it's it's part of this sort of idea of we're trying to include physics in some of the longer term, the data sets that we would be doing such things with. And so just to kind of give you an idea of how big of an effect these phonon effects are, even at zero temperature, there are sort of 0-point effects. And so this is a zero temperature plot. And on this axis, we have the computed binding energy with the state-of-the-art with two different levels of theory. One is sort of the state of the current state-of-the-art, and one is adding the phonons. And what you can see is that if you compare the computed binding energy and the measured binding energy, well, all of them are a little too high. But if you include the phonons at 0 Kelvin, then, at low temperature, you're doing better. I should also instantaneously say that measuring this quantity is not that easy. So there's an error bar here. So I haven't put that on there. I agree. I don't, we could be closer, we could be further away. But the idea is that it's bringing this value down. And it's also interesting to see that the current state of the art is kind of that far up. The other thing we've been able to do with this methodology is to compute the temperature dependence of this quantity. And I want to show you an extreme example for an energy material. So bismuth vanadate is a water oxidation photoanode. Basically, it's a light absorber, but it has, it's in this sort of, it's being explored for solar fuels or artificial photosynthesis applications. And so it has some special requirements. It has to be, stable under water oxidation conditions, and it has to be stable under bias, and et cetera, Porbet diagrams, et cetera, et cetera, et cetera, won't go into it. But essentially, there's some criteria that it actually satisfies. So it's interesting, but it's an oxide, so an unconventional semiconductor. But the state-of-the-art theory predicts that it has an sort of exciton binding energy of about 100 MeV, which is a few factors above KT at room temperature. And so you might think, well, this is, I'm going to have a lot of recombination. I'm not going to be able to separate the electron and hole. But it turns out with the sort of approach we're using, we can predict, it's kind of funny, I'm leaning back here, but you can kind of predict that there's a large reduction in the binding energy at room temperature into a range which is sort of more suggestive of where you might imagine that separation is more probable. And this very large reduction has to do with the fact that there are multiple polar phonon modes that are very low energy, about the energy of the exciton. And so essentially you've got a polar phonon that is oscillating about the same period as the Bohr orbit. And so that really reduced that. There's a strong interaction there, frequency-dependent interaction there that leads to this reduction. The other thing one can do, and this is another example of an observable, is calculate the exciton dissociation rate. And so this is when you create an exciton with a photon, then that exciton can scatter with different excitons and gain some finite center of mass momentum. It can also decay into via other channels. What we would like it to do is decay into a free electron and hole pair. And we can do that. We can compute the probability of that and sort of the lifetimes associated with that as a function of temperature with this formalism. And so you can sort of see that there's a sort of picoseconds to femtoseconds change in the lifetime as a function of temperature, really kind of suggesting a highly, very ready dissociation. And one of the things that's kind of interesting is that even at zero temperature, there is a channel by which you can absorb a phonon and it will decay into an electron and hole. And you might be like, well, at zero temperature, phonons aren't there's no phonons available. Well, actually, though, this is an indirect gap system, and so there is a channel by which phonons can absorb and emit. Emit, not absorb. So that's kind of so it's sort of an interesting. So for indirect gap systems, you kind of have both of these emission and absorption channels available. And then this has a kind of a consequence for observables, and let me say a couple of comments about that. But there's so this is an optical absorption spectrum. It's sort of a linear absorption spectrum for this system. And so you can sort of see if you introduce these finite temperature effects, the absorption spectrum gets a little bit closer to the experimental spectrum. But without the finite temperature effects, you have this very strong exciton peak, which isn't seen. So it's not, a perfect agreement, but I think it kind of shows you the impact of including these effects. So kind of finally, I wanted to come back to the halide perovskite for a second, and just try to show you another kind of a benchmark, if you like, to compare this with some experimental data, the physics I'm just describing. And so this is an optical absorption spectrum for halide perovskite. So the red curves are at high temperature, and the blue curves are at low temperature. This is an experiment. It's an experiment done by this Oxford team. And so with this data set, one can one can fit this data, extract exciton binding energies, and plot that as a function of temperature. And so this is that's what the gray error bars are, gray data are. And what we can do is kind of look at the different components of how phonons change the exciton. The screening, which is in orange, and the renormalization of the individual electrons and holes that the exciton is composed of, that's in blue. And really those two effects in combination are what are giving rise to the experimental trend. And what is very interesting and kind of important is that the screening part is really the dominant trend. So essentially, to take a step back really quickly and think about the hydrogen atom, phonons tend to localize the electron and hole, increase the effective mass, increase the binding energy, but the electron-hole interaction is also screened by the phonons, and that screening dominates in this system, and that gives rise to this reduction in the binding energy. So this is a work we're preparing. So this kind of ends part of this talk where I just wanted to, there's no machine learning at this point, there's no AI, but basically, giving you a sense, we're still trying to work out how to calculate and predict accurately some of these spectroscopic properties. And part of that, I don't think that kind of research can go away right now. So I don't think because we're not quite there, and so I won't tell you how much CPU time we used on all this, but it is, and also, brain time. So one thing, let me just shift and talk a little bit about the data sets at this point, and kind of seg into that. And so here is my, one of my favorite databases, because it's Berkeley, and we're anyway. But this is this is one of our favorite databases, and love it very much. Can't get enough of it. It is, however, it really doesn't have more than kind of ground state DFT properties for them. So I think. And even with more advanced functionals, we can start, the alphabet soup will come in a second, but R2 scan, et cetera, that's not enough to really predict spectroscopic properties. So I think there's a real opportunity here. This is not necessarily a deficiency per se in that, you have to start somewhere, and they've really got there's a terrific data set here, but that's a deficiency. And so one of the things we wanted to do is use density functional theory to predict some of the things that I just showed that were predicted with beyond DFT methods. And so I'm not going to go through a reminder of DFT for you, but basically it's a way of getting the ground state energy as a functional of the electron density, but the functional isn't known and it's approximated. And that approximation leads to this alphabet soup of PBE and other things. Basically, there are different classes of functionals, exchange correlation functionals, which are the approximations, and some are these sort of generalized gradient, semi-local, and some are hybrid functionals. And these hybrid functionals include some exact exchange. Now, the DFT band gap, as has been pointed out, is the gap computed from some of the quantities that come out of a DFT calculation. Is underestimated, and there's good physical understanding of that. This is I think the first calculation of DFT band structure for silicon. Yes, that reference is 1982. That's exactly what it is. I was 8 years old, and your parents were 8 years old as well. Basically, I didn't know about it when it came out, so I only learned later. But basically, this is off by a factor of 2. And there's a really good understanding of why that is, the so-called derivative discontinuity. It turns out that hybrid functionals allow you to get around this a little bit. So a hybrid functional doesn't have this derivative discontinuity, at least in principle. And so what we've been able to show in recent years with some collaborators at the Weizmann Institute is that we can develop a sort of a non-empirically tuned hybrid functional that predicts very high-quality band gaps for a wide range of semiconductors. So this is a plot on the left of gaps that are generated with this method versus experiment. And the MAE is really impressive. This is about 25 materials, and the data set now is like 40 or something. The real limitation is the reference data. It's not easy to measure this gap. So this is a very hard measurement. You have to remove the phonons, you have to remove excitons, remove stuff, and so that's a little bit of a limitation, but it looks pretty good. And so the way the functional works, I'm not going to get into it very much, but essentially what you do is you evaluate the exchange operator exactly, and so you 1 over R. And so you rewrite 1 over R with the identity shown up here that introduces 3 parameters. And then you tune those 3 parameters to satisfy boundary conditions and theorems of DFT as best you can. And so we have a way of doing that, and that was a little bit of a challenge, particularly for some of the theorems involving electron removal for solids. Got around some of that. I can talk more about it. But if you use this, and it's on a per system basis, so each material you need to do this, then you kind of get the results on the left. And the other sort of state-of-the-art theory in this space is GW. I showed you some GW results earlier. And what you can do is you can use this functional as a starting point to do perturbation theory. And what you find is that there's 0 perturbation. So GW correction is 0, or small, And so that suggests that you're basically done without the GW calculation. And so in addition to some of the, we call this affectionately Watt. It's 1 ear optimally tuned. We can talk about what that is later, but Watt. So that's the functional, and it does work pretty well for perovskites, not just garden variety semiconductors, and I'm actually showing band structures and not gaps here. It also works pretty well for bismuth vanadate without introducing phonons, of course, which is needed to capture more of this peak shape. But you can sort of see this is the state-of-the-art GW and BSC, and this is sort of the Watt value. So you're getting kind of spectroscopic information, but at less computational cost. It's still a hybrid calculation, but it's less computationally complex and costly than a GW calculation. So one of the things we've also done recently is to develop a workflow to kind of generate the parameters per material in a somewhat, we call it minimally supervised way. It's not unsupervised. And so just this is giving you a little bit of a sense for, so we can generate these parameters pretty quickly in an automated fashion. And what we've done is look at about 320 of them. Now, we don't have experimental data for these, so we're just looking at their gaps. But this just gives you a little bit of a test we just take structures from the materials project. And this gives you kind of a glance at what kind of data is coming out. So this is the predicted gap on the left axis, and then on the bottom is the PBE gap in the materials project. And so you can sort of see the trend that PBE is underestimating the gap. But you can also see things like, if you pick a value of the PBE gap, there's materials with very different hybrid gaps. So the point there is that you can't just say, let's just multiply each PBE gap by 2. That doesn't work. It's not a simple theory, which is a function of the correction is not a simple function of the PBE gap. This is relative to HSC. It's another alphabet soup type of functional, but this is does quite well for the optical properties of materials that are in the visible, with band gaps in the visible. And so you're sort of seeing that there, but again, there's some scatter there, and it doesn't do as well for larger band gap systems. Now, just to take a couple examples in this set, which is sort of random, But it turns out that, unbeknownst to us initially, there is some connection to some other work we were doing in the group, so I just want to show you there. There are some there's some data here in red, and if you kind of zoom in, it's scattered here, and these are these data in red. These are material, a kind of an interesting class of layered materials, the zintels, and so this is they kind of consist of usually a rare earth, a column 2 cation, and then planes of tetrahedra that involve a metal like zinc and a pnictogen like nitrogen or phosphorus, phosphorus. And so this is an interesting class of materials that has been recently proposed for water oxidation, photoelectrochemical water oxidation, so solar fuels applications. And so this is not our calculations by Geoffroy Hautier's group at Rice, but they find that, for example, calcium cadmium phosphide has a direct gap in the visible and a pretty interesting associated experiments, PL, a very sharp PL peak, which sort of suggests that it's defect tolerant and really photoluminesces as well. Looks promising, like halide perovskite. Now we've done some work on zinc titanium nitride, separate material, and so we wanted to look at, which is in our data set, some nitride-based, zinc-based materials. And again, part of the issue with these photo-oxidation catalysts, water oxidation catalysts, is that they have to be stable, they have to be compatible with passivating materials and such. So we were taking a little bit of a hint. This is again part of this is what we're putting into our prompt still. We're taking a little bit of hint from our intuition on previous systems, and kind of zoomed in on these calcium zinc nitride materials. I'm just going to give you a couple of preliminary results. This isn't published, but you can sort of see for the calcium zinc nitride material on the left, it's a direct gap system. The phosphide is an indirect, just slightly, and it has very low effective masses, a reasonably low band gap. Interestingly, GW, if you look at the fine print here, GW does not quite predict the, excuse me, this is what I was like, doesn't quite predict the experimental gap very well, but it does improve. The WOT functional does a lot better with respect to the experiment. So these kind of more challenging one-shot GW calculations sort of aren't as effective for these systems. We can also look at the excitonic properties of this system, and you can sort of see that there is a very sharp exciton. There's also, it's a layered material, so there's a polarization anisotropy. So there's a sharp exciton, but it's only 20 MeV. So this could be a very interesting material for applications, particularly if it's kind of pore base stable, which is something we have to check. So we're not done with this study, but this is another example of a way I think we may be using data science, which is, large survey with an accurate method, zoom in, and some, higher, resolution, higher accuracy calculations. So I think I have a few minutes left, and I hope I do. And I'm going to switch gears, and I'm going to talk a little bit about porous materials. And so this is really a completely different topic, but they're relevant for energy in terms of separating elements and molecules. Carbon capture is one very interesting application. And one of the things I'll show you is we're trying to use machine learning to help us predict the structures of these pretty complex systems with a lot of degrees of freedom and a lot of low energy modes. So, where if you think about it, and if you've done any of these calculations, a structural relaxation will trap you in a local minimum. So we're trying to, this is the way we've been using it up to this point, or one of the ways. So let me say a few things about CO2 separations and porous materials. So one example of a porous material is metal organic framework. These are consist of molecules that are linked by metal cations coordinated in a certain way. And depending on how they're coordinated and the type of ligand, you can get all sorts of topology. And at this point, Omar Yagi's picture should be up here, and the slide is pre-Nobel was made before his Nobel Prize. But essentially, it's an important class of materials according to Sweden, anyway, and others. And me as well. And so they think there's kind of a lot of opportunity in trying to, because they're very porous, and you can tune the interior, there's a lot of opportunity to try to do selective filtration or capture of trace elements or molecules. And CO2 is one of them. So one promising system for CO2 capture has been an amine-appended moth. And this is actually work we've been doing in long-time collaboration with Jeff Long. So here, the basic idea is you start with a moth as shown. So it's a hexagonal honeycomb framework. And this moth has metal, what we call open metal sites, these exposed under-coordinated metals. And so if you flow gas through this, a lot of components of that gas will try to stick to the metal. It'll stick to the sides. There'll be some van der Waals interactions on the side, but there's also an opportunity to kind of more strongly coordinate potentially with the metal site. And so for capturing something like CO2 or any other specific molecule, that could, on the face of it, be interesting, but it's also maybe a little bit of a challenge because you really have to tune that metal site in some way to specifically capture the molecule you're looking for. And if it's CO2 or nitrogen or arsenic if you're trying to filter water or something, so the real challenge is to kind of, so the way to do CO2, or one effective way to sort of capture CO2, is to drop or sort of append, graft a diamine molecule onto it. So these diamines bond strongly. So one end of this diamine, bonds very strongly to the metal, and then the other one is exposed, and that can react with CO2. And there is a well-known, CO2 amine interaction, and in bulk industrial contexts, usually CO2 is captured within amine solution. So there's sort of a precedence for this. So the idea is this is just a cool movie, but the idea is to append these amine groups to each one of the metal centers. And then now you can imagine riding on a CO2 molecule through this which one should I choose? And so that's sort of the idea. And so, yeah, this is now looking, the pore is in this direction, pore axis is in this direction, and CO2 kind of will attack this. And what CO2 does, it does a few different things, and I'll show them in a second, but the first thing it does is kind of attack the amine metal bond, and that leads to this kind of complex formation, this carbamate formation. And so it turns out that there's a very, this is sort of verified by X-ray diffraction and calculations, but CO2 displaces the amine, and then there's a proton transfer, and that enables the next CO2 to more readily displace the next amine. And so there's a cooperativity that is going on here that leads to a finite chain along the pore axis of bonded CO2 and carbamate. And the consequence of that is that the absorption profile is non-Langmuir, and so it's a step function. So this is absorption versus pressure. So you imagine turning up the pressure of your gas, and once you hit a threshold, you go from empty moth to full moth. It's like a diode. So, and that's not Langmuir-like, and that is a direct result of this cooperative behavior. So now this threshold can be tuned with temperature and pressure, but it also can be tuned chemically with the ligands. And so this is just different amines with, so this is an amine, this is a diamine, diamines that have these different, kind of appendages and structure, and that, depending on what that is, one can, change the threshold, and one can actually even achieve regimes where you're seeing the absorption under atmospheric conditions, 400 parts per million, or natural gas, flue gas, or coal flue gas. So if you wanted to do these materials aren't commercialized, scaling them, other issues, but they actually have tunability in the range of interest for doing carbonate capture applications. So one of the things we've been interested in is using the machine learning interatomic potentials that were discussed earlier to sort of study the structures of these to predict some of the dynamics of CO2 insertion. And what I want to do is just close with a new structure that we were able to predict with this that is a little partially unverified yet. So I'll just try to be provocative. So there's just a few more slides here, but basically the first thing I wanted to tell you, so to help you kind of follow what I'm about to say, is that there are multiple ways CO2 can actually bond to an amine-appended moth. So one way is sort of, so if you like Lewis structures, is this sort of cooperative chain formation along the pore axis. But actually you can also, CO2 could also attack this nitrogen, and as long as there's one up here, then there's sort of another stable structure, which is a carbamic acid structure. And depending on the topology of the moth pore and the nature of the amine, you can get either the chain or the carbamic acid. Okay. And you can even get both. You can get a mixed regime. So it's kind of fun. And a lot of this work to figure this out was done with Jeff Long and also Jeff Reimer with solid state NMR. And there were 3 Jeffs involved. It was amazing. So there's some tunability in how CO2 can land. And so what we built, we kind of building on that, my group sort of asked, well, what if you have a triamine, essentially? What if you have 3 of them? And would there be a way to increase the number of CO2 per metal site? So just increase the load that you could absorb. And so with that triamine, you can actually, we thought, perhaps have the best of both worlds. And that's what we were aiming to see. And the thing is that, now you've got a moth with 400, there was an atom survey. I can't remember, I think Professor Schindler had an atom survey at some point, so how many atoms have we done calculations for? Anyway, I actually don't remember, but the various stressful, so these moths are about several hundred atom unit cells. You add the amines, you add the CO2, and there's a lot of possibilities. And the amine ligands themselves, the linkers themselves, have a lot of low energy degrees of freedom. So relaxing a structure like that with conventional methods is pretty hard, and also pretty hard to convince yourself that you're in a ground state, you're in a global minimum. And so basically what we did is, just to cut the long story short, is we used an MLIP and simulated annealing to essentially find the global minimum of one of these structures. So I don't have to talk through this in any detail. I think we're using machine learning interatomic potentials. I can talk more about the ones we use and how we do, but it's a bespoke one. It's not a foundation model. And that allows us to, as we heard very nicely, evaluate energies and forces with linear scaling. And in this particular work, we built our own MLIP, and so I think we could do better in 2026, but it's a pretty good. I will say this was cheap to evaluate. That was the evaluation time was relatively cheap. And essentially, the way we did it, though, was with substantial training. So we trained on about 30,000 structures, and that was kind of one of the biggest parts of this. We also had to identify an exchange correlation functional that gave us good accuracy. So that's a very important part. So our ground truth is critical, and we're looking for 5 kilojoules per mole, and that's actually quite stringent. And you can pick functionals that don't get that. So there's part of this is always the ground truth. We use an active learning scheme so that one nice thing about these structures is that even though they're a large number of atoms, for anything our MLIP generates, we can always do a static DFT calculation and check its energy. And if it's sufficiently different, we can add it back and retrain. So this kind of gives you this sort of a punchline here, a couple slides. What we found after doing some simulated annealing with this potential is that it turns out that when you introduce CO2 into this environment, it doesn't displace a metal atom. It just bonds in the pore, and it bonds in a very strong way with, you can sort of see 5 hydrogen bonds involved. And so we have this kind of ammonium carbamate formation, but no metal site displacement. So this is an unusual structure that hadn't been seen experimentally. And it's very interesting. It has a very high binding energy, but unfortunately, the binding energy for additional CO2 is very small. So it doesn't look like you're going to be able to put more than half a CO2 per metal site, which is actually a step backwards. Now, it turns out that this system had not been then seen, but we asked the Jeffs to look into it, and they found some strong evidence of this kind of structure, in comparison with our NMR chemical shift calculations. So there's some evidence that that structure exists, and so that was good. So that emboldened us a little bit, but of course it's disappointing in the capacity. But it turns out that so what we thought, we'll just disrupt the network of hydrogen bonds by introducing a methyl group, and then lo and behold, that does lead to a much different situation, where you can support actually up to two CO2 per metal site, and the sort of structure that we were looking for. And one of the things notable is the predicted energies of binding are roughly the same, and that suggests we can, the structure will, potentially absorb as much as that. That hasn't been confirmed yet, but this, I kind of wanted to leave you with this structure in that this is a very hard structure to get with the energy minimization, and it was a lot of kind of simulated annealing plus this MLIP that allowed us to predict this structure. So I will say in more general terms, we are thinking about the whole area of crystal structure prediction is another interesting one, and MLIPs can accelerate that, but there's still this issue of getting out of local minima. So maybe I'd take a step back. A standard relaxation with density functional theory to try to find this minimum would be very difficult. Okay, we agree. But even a standard relaxation with an MLIP would be very difficult with this. So we needed to heat the system up, explore the potential energy landscape, and find this minimum. I think there is a potential even to kind of go over to the crystals in crystal structure prediction. One may be able to use similar ideas. I think, especially for these kind of porous materials with a lot of low energy degrees of freedom. Okay, so I think I think I can summarize now as just saying, we've been, starting to use these data-driven methods, and AI is coming for us, I think kind of, in my view, it's really important. The AI is only going to be as good as the data that it's trained on. There are a lot of observables that we're still learning how to compute with decent accuracy. I think many of there's a lot of data in the materials and chemistry community, including non-calculated data, non-theoretical data, experimental data, that isn't really organized in a good way for AI to make best use of it. So there's a lot of challenges ahead. But also, there's some pretty cool stuff going on, especially, this sort of, these surrogate models for DFT really can speed up dramatically, DFT calculations for more complex structures. They're really good for energies and forces, but then, I think a next step for us is really kind of extending those to properties that are really beyond just energies and forces related and their derivatives, electronic properties and such. And so, I sort of see that happening in the next several years, but we're not there yet, but I think it's quite promising. So I think with that, I'm just going to thank the collaborators and students and funding and take some questions, I hope.
Thank you. It was a really interesting talk. I guess I start with my last question. So for the project that was focused on CO2 absorption, when you use the tertiary amines and you have this really strong bond with the CO2, what about the absorption? Like,
right.
Is that?
Well, and so, you know, the thing, yeah, I guess what I'd say is this, so what I would say, these energies, yeah, I don't have to point to it, but these energies are quite large. I didn't really give much context for these energies, but what that would end up doing is it will push the desorption to higher temperatures or pressures. So your isotherms will just shift. And this is really out of a, you know, so this is good at some level for, you know, direct air. I mean, if you wanted to grab stuff out of the air or something, but then it would be very energy intensive to empty them off. And so I think that's why, you know, that's another reason to steer clear of this. So I would say this regime of, you know, this is still a little high. One can do these kind of calculations, but you know, aiming for something a little lower than this 30, 40 kilojoules per mole is sort of what we would be looking for to kind of balance the energetics there. But yeah, that's the issue of, you know, emptying them off. So this is reversible, but at what cost? Yeah, so yeah.
Thank you. And the other question that I had was about the phonons, the emission spectra.
Yes, yes.
So the emission spectrum, the lifetime, it was lifetime versus temperature.
Right.
I was wondering, was that for the phonons or excitons? Because I know that we can measure it for the excitons using time-resolved photoluminescence, but I was wondering how you measure that versus the temperature.
Well, okay, so that's a good question, and I mean this will contribute to the line width, the physical line width of a measurement, spectroscopic measurement. So this would be, you know, it's, you know, lifetime, et cetera. But this is one scattering channel, if you like. So I think this particular one is. I would hesitate to say it's measurable, but maybe I could aggressively say you could probably isolate it, but it wouldn't be so easy. I think, you know, the thing for us would be more like, and let me kind of follow up with the question that you might ask here as well, which is, you know, we've shown this process and this, like, if you like, scattering channel, you know, what the rate is. What are the rates of the other scattering channels? Because, you know, you may wonder, is this relevant? And I mean, I would argue it's pretty fast, actually. It's so fast that the perturbation theory we're using here may not even be valid. I mean, it's really quite a fast, especially at room temperature. But there are exciton scattering rates that, you know, as soon as the exciton acquires center of mass momentum, then, you know, you're sort of no longer you know, radiatively decaying, but there's radiative lifetime, that's also much longer. There's Auger process. There are other ways, there's other scattering channels that aren't being computed. But I think, you know, this is what I would say from our model calculations. We haven't done full ab initio on those things. This is definitely a fast rate compared to those. I mean, certainly radiative lifetime, but certainly a fast rate. So, and like I said, I think this is a little bit novel in that, you know, we're also able to decompose this emission and absorption channel and, you know, kind of see a finite lifetime even at low temperature. So I think that could be, maybe that's something that could be probed. So one thing I should also say, this is one state. This is the lowest lying exciton. There's another one, and another one, another one, and your measurement has to resolve those as well. So it's a tough measurement by, you know, I'm sure you can do. I'm sure if you're measuring, I don't want to imply, but I'm sure you could do it. So I'm just saying, like, it's more of a caveat on us. You know, there are multiple states, and I can imagine them being brought into a. So if you look at this, for example, this is dominated by one state. That peak is dominated by one state primarily, but you could ask, well, how many? What is the next one? And, you know, it's a few MeV. You know, it's 20 MeV away or something. So yeah.
Thank you.
Yeah.
Hi, that was really interesting. So my question comes from the perspective of an organic synthetic chemist.
Okay.
And so this may or may not be something that you would be interested in. But I'm curious, we have spent a lot of time finding very cool diamines, triamines, all kinds of amines for
Yes.
catalytic chemistry, like with copper, for example, CN coupling.
Yeah.
And we've created very interesting databases of these
Yes.
ligands, and we have all of this high throughput data for example, CN couplings. But I'm curious if there is a way to sort of is any of that data, or is any of that experimentation that's been done and all the results have been found out about how they interact with in small molecule catalysis, can any of that be used when you're then trying to apply it to MOFs, for example? So you're not starting completely from scratch. You have some experimental
Right.
data. Is it useful at all?
Yeah, so I mean, I think that's a great question. I'm very interested in it, and I think it's, yeah, yes. So I think it would be, and it's a challenge to perhaps, but a very good one to incorporate these different kinds of data sets from different, I mean, maybe, I think one of the things that I'm getting from your question, I mean, maybe there's some experimental information, there have been other calculations, those calculations are at a different level of theory than I'm doing, there's my calculations or whatever. How to use all of that information in the right way, in combination, in a model, in a predictive model, I think that is a really interesting question. And we should, in some sense, I guess as you kind of are getting up to speed in a given field as a researcher, and I'm still getting up to speed in my field, and I've got 25, 30 years already. As we do that, we integrate that information somehow. And so, these models, multi-fidelity data sets, where you have these different levels of theory incorporating, that's an exciting frontier. Maybe other speakers want to comment on that, but I think the right thing to do would be to try to integrate that information in the right way. But I think that's still a research problem, how to do that. So, yeah.
Really beautiful talk. I have a simple question for the second part. And so you talked about CO2 absorption. I'm just curious, in realistic applications, do you have only CO2 in the gas? And so what about other components that might compete and all that?
Yeah, so that's a great question. And so yes, generally in flue gas you have a lot of different stuff. As an example, in air you have a lot of stuff. So if you, so I think the key part of so I think this area of porous materials and adsorbates, it's really interesting because you target CO2, so the system has to be selective for CO2 and it has to let everything else pass through. And that's essentially what was designed into these amine diamine ligands. So that they're just highly selective for CO2 and they let other things pass, and that includes water. So if you have a water molecule and you have CO2, well, the CO2 is reacting with this, and the water molecule, actually there are studies, including some we've done, that have shown that CO2 in the presence, under humid conditions, binds even better to these. So, but I think that it's more of a general sort of area of interest, which is, can I design the right appendage to capture a specific thing? If you want to decontaminate water, you may want to take trace elements out of it, so you have to design a ligand or something that would bind that, and hopefully let the water go through, for example. So I think that's a great question. But in this case, it turns out these amines are highly selective for CO2.
Great talk. I don't want to ask a long question because I'm keeping everyone from lunch. But I found the WOT quite interesting on the band structure calculation. Yes. 2 questions on that. You mentioned for each material you need to kind of retune those parameters. Overall, how expensive is this compared to HSE and GW?
It's basically I would say the tuning step, let me try to get it. It's like 4 hybrid calculations right now.
I see.
To tune it.
Okay, that's actually quite
So that's better than GW, but it's not better than HSC.
I see.
So, so I think first of all, there is an opportunity to machine learn these parameters.
Yeah, that makes sense. Yeah.
So,
Okay.
and I think we're finding that might be a way around this. And then I think there's also some delta learning that we can try to do to predict the watt gap without even doing the evaluation. So, so that is an active area of interest. I have to say, you know, for the density functional enthusiasts in here, I don't know if there's any left, but for those who are still around, you know, there's some. I would say we're still exploring the limitations of this functional. So I don't want to come across, well, this functional solves everything, and you know, so this is again maybe a lesson for the data science side. This science, I think it is promising to jump in and do some data science here. Let's start machine learning the heck out of it, but there are going to be materials for which this is not a good approximation, and I don't think it's a 3-parameter self-energy correction, if you like. So I think, but having said that, it seems to work well for oxides, and even 2D layered materials. And so, you know, we're really now doing, this is sort of my own perspective, like 2 parallel lines of work. Can we make this more efficient with machine learning? And can we, where does it break? Where does this approximation break, and how can we improve it? And both of those have to happen, actually.
The follow-up question, do you have a sense for how this affects effective mass?
Oh,
not just band gap.
No, it's got a big effect on the effective mass. Okay. Actually, so you know, it turns out this actually I didn't talk about it. So it's tuned for band gap. So the theorem, the IP theorem from DFT, again, kind of for the aficionados, but that doesn't guarantee the other eigenvalues are relevant. But it turns out that the band structures, I flashed a couple, but they're pretty good. And the effective mass is very different, and that is because exchange tends to stretch out the band structure. So you won't, and you know, there's some screening in there too. So yes, I think it will be interesting to tabulate those, and they will be different from PV for sure. Yeah.
Great, thank you.
Are we out of time for questions? Okay.
So we're moving on to lunchtime, which is all set up, but my announcement is for my NRT cohort students and our speakers that have spoken or are going to speak, we'd love to get a picture out on the terrace. So if you guys can move over there, everybody else, please start enjoying lunch.
All right, thank you.